Good afternoon. All right, Monday again. In 1 week, midterm 1. 6:30 to 8:30. It's a 90-minute midterm, closed books, multiple choice answers. But you have to bring your calculator, your TI something or whatever this is, that simple calculator, and you get all the constants and formulas, and you get a periodic table. So I would make use of the weekly review sessions that has been going on. Greg Dellinger, the head TA, gives on Thursdays from 5 to 7. Right here, the review session would be advisable to come at least before the midterm to the one. Okay? There are also drop-in office hours. If I could have your undivided attention, that would be great. There are drop-in office hours. They're around the corner here in B12, actually, Latimer Hall, not 12B, B12 Latimer Hall. And there's supposed to be a schedule posted at the door. Unfortunately, I don't see it. I will talk to the people responsible to post that schedule. From Mondays to Fridays, there's always somebody there, okay? From 10 to 3. You can just go, discuss science, and ask questions. I also recommend the Student Learning Center and study groups that you can do between yourselves. In addition, there's the ASUC. They make a reader, I think. Here's the reader, the note taker. You can sign up for that. And if it's not enough, what we give you on the B-Space on the web, if this is insufficient, you can even get a reader. All right? So we do whatever we can to get you fit for all this. Even in the lab, there's review and discussion. Okay? So this week, the lab is review and discussion. I think it's about absorption spectroscopy. But having said this, we come to a review of last week's lecture, last Friday's lecture, and we were talking about the electron. And we've seen that we know that the electron is a particle. It has mass and charge. But we also have seen we can treat it as a wave. It is also as a wave. So we had here a rope, went from here to Karen over there, and we would be having a particle in a box. This is our box. The walls are the box here on the side, the box walls. And so we said that rope, the wave function of that electron, because we are considering it as a wave. Good morning. We're considering it as a wave. That wave function has to be 0 here and has to be 0 over there. And if you have that rope here straight, there is no wave function on it. Okay? So it has no energy. The first possible wave description that you can have was 1/2 wavelengths. Remember that? There was one lobe. With this, that would be the lowest energy state that the electron could have. Okay? And we call this the ground state, and we give it the number. If you have one lobe, you have the quantum number n equals 1. There is no quantum number n equals 0, because the electron will always have energy. So that means the lowest possible waveform it can have is that half lobe. Now we could put a full wave on it with 2 lobes, and we had one thing in between where it went through 0. You've seen that the wave function went through 0, went up and down, and it was essentially, in front of me, it was 0. So the wave function went to 0. We called this point a node, where the wave function becomes 0. So if we have 2 half lobes, what's the number for n? N equals 2. That's the main quantum number, 2. And the number of lobes is n minus 1. So we have n equals 2. The number of nodes is n minus 1. So the number of nodes would be n minus 1, would be 2 minus 1 is 1. All right? So we went on then, and we have here, this is how the wave looks itself. This was the ground state. You see that the electronic state, the lowest possible electronic state, n equals 1, you had no nodes. This is the first excited state. This is our energy scale here. Here's the energy, the lowest possible energy, and then the energy goes up here, okay? So that's the quantum number 2, the first excited state, or the second state. This would be the ground state, this would be an excited state. So the electron in this state has a higher energy, okay? I can put it in this state, then it would have this energy here, or it's in the first excited state, or in n equals 2, then it would have a higher energy. Just look at one electron, okay? We can put it here, we can put it here, but we can also put it here. Then it would have even a higher energy. And as we go higher and higher, the energy increases. We go to n equals infinity, we can actually go. That's called the continuum. So you have n minus 1 is the number of nodes. You have 3 lobes and 1, 2 nodes. That means the wave function goes to 0 here. So we have seen there are different energy levels, and we know that the energy of that electron is quantized. It only can do specific levels, all right? So, and you can't have, it has to be whole numbers of n. You can't have n equals 4 1/3 because the condition will not hold, that it has to be 0 here and has to be 0 there. Now let's take it off the wall and put it together. The 0 has to match the 0, okay? Otherwise you won't have a standing wave around this nucleus. And the standing wave itself is in this case some kind of a circular orbit, but there are many, many other ways how the standing wave would look like, and this is what we're going to talk in this lecture and the next lecture about. So we have an electronic system. Let's say we have an atom that has electrons. And now there is the possibility, if I give energy to that atom, that the electrons will pick up that energy and will go in a higher state, or in even a higher state. So they will pick up the energy and go into a higher so-called excited energy state. Do you follow me? Okay. So, but we know this is quantized. Only certain amounts of that energy gap, you need to have a certain amount of energy to come from that level, for example, this level, from the ground level to this level, or from this level to here, or from this level to here, or from this level to here, and so on. So it has to have a certain energy. Now we talked about the absorption of light. So the electrons can absorb light, and the energy that the light impacts to the electron will be taken up, and the electron will have that energy in a higher state. Is that clear? Now let's do this. And because it's quantized, only certain energies, only certain wavelengths will fit for this specific atom. This is different for each different atom. And it will fit for that atom. And now let's assume with this particular atom, this has these kind of energy levels. That's an atom, and we want to excite the electron with light. So we shine light on it. And what happens is, so I shine this violet light on it, nothing happens. Because the energy of the light and that gap, that energy gap between the levels is not the same. So it doesn't fit. It doesn't have the right energy. So it needs to have the right energy for it to interact with that electron. Now I do blue light. Blue is obviously a very high energy light compared to red. Red is a much lower energy light. Red has a longer wavelength. Blue has a much shorter wavelength and a higher frequency. So that means that it has a large amount of energy, and this fit here to go from level 1 to level 4. It it took that electron from level 1 to level 4. Okay? Now that electron is in the third excited level, or in n equals 4. It went from the ground state, n equals 1, to n equals 4. So this is the first possibility. And now, since it absorbed this light, it's missing in your spectrum. You will, if you look at your spectrum, you see that it's missing here, okay? That's an absorption spectrum, a line absorption spectrum. It misses this line. So if we want to go, for example, from here to here, we would have to go to a little bit longer wavelengths or less energy because the gap is smaller than from 4 to 1. We go from 3 to 1 or from 1 to 3. So we would, for example, have something a little more to the right here, more at higher, longer wavelengths. So this green here, we used some green, it didn't work because the energy is not right. It doesn't fit that gap here. There it is. So this energy of that green light, which we know, the difference in energy from here to here is h times the frequency of the green light. And so it fit, it promoted, it took that electron from the ground state to n equals 3, or the second excited state. First excited state, second excited state. Now let's see what else can we do. We can go from here to here. So we would need something even with a longer wavelength or a smaller energy, and it also has to fit. So the delta E has to be h times nu, the right frequency of whatever the wavelength is. There you see, this yellow didn't work, so it was somewhere here. We have to go somewhere here to red, and there it did work. So delta E is the difference between this level and that level. The energy difference is h times the frequency of the red light. All right? So this is how a line absorption spectrum looks like. Now, let's assume, or let's just discuss, now these electrons are in these excited states. But in chemistry and physics, everything wants to go to the lowest possible energy state. If you don't give it more at the energy constantly, it will not stay in these states. So what it will do, if you switch off your light, it will become light itself. It will take that electron from this level and go back down to the ground level. And when it does that, it will emit light, and this is blue light. That's exactly that energy gap again. And you will see an emissions line. It emits that line. It emits a photon of that color, or photons of that color. Okay? Now, we go from here to here. That would be green light. It would emit green light. Boom, there you go. And it shows that emission line. And we go from here to here. What would be the color? Go from here to here. Would be red. And if this is our wavelengths here, it's the longest wavelengths. So this would be the emission spectrum of the particular, very specific atom. Okay? That's a specific atom. You can identify atoms by looking at their emission spectrum. And different atoms have different emission spectrum because they have different energy levels. All right? So this is a tool how you can, for example, identify elements. You do an emission spectrum. So, for example, you put salt on your stove, and it's going to be yellow. So it emits yellow light. It emits, and you have potassium. I think potassium is reddish. Yeah, so it emits reddish light. And you have strontium is also reddish. It's reddish light, and then there's some green, some others. So this is specific. This emission spectrum is specific for each element. And with this, you can identify them. Let's make an experiment. Is the lamp on? We have here, mercury is at room temperature is a liquid, a very heavy liquid. You've probably seen that. Yeah? It's poisonous actually. But if it's in a lamp, it's a different story. So we take mercury and we heat it up. Just put temperature in there. You can also excite something by heating it up, okay? You don't have to put light in there, because light is also a specific form of energy. We just heat it up, all right? So now you get the sodium atom. No, is it sodium or mercury? Mercury. You get this mercury atom. That mercury atom in excited state, not the atom. The electrons are in excited state, okay? And so you heat it up on the bottom, and it will look like this. This very brightish light will be emitted by the mercury atoms, by the electrons of the mercury atoms. And they come down from these excited states, and they go back up and come down, back up and come down. This is how you see that this light is so bright. Now let's have a look what we can see here in the spectrum. We put here's our light, we put it through a slit, and then we have a diffraction grating. You know now what a diffraction grating is. We spread out the wavelengths, and you can see there are 3 wavelengths. which make that white light. This is that yellow here at the longest wavelengths, that green, and here you see that blue. You see it here? There, the blue. So there are three wavelengths emitted, which if you combine them, make the light look like it is, that bright color. But there's another one which we can't see with our bare eyes, and I have a fluorescent screen here. Half of it is fluorescent, half of it is not. So I'm going to look here. Where is it? You see it? See, what would that be? What kind of light? This is violet. That would be then ultraviolet light. So we make it visible by putting it on a fluorescent screen, and then it acts with the fluorescent dye, and we see it. If we don't have the fluorescent screen, we can see it. So there's actually 1, 2, 3, 4 energy levels that emit electrons into the ground state of the mercury atom. All right, thank you. Let's have the lights back up. So if I would have another compound here, it would have a different color. So let me ask you a question now. We have an energy level scheme of an electronic system, and we're dealing with one electron, okay? Just one electron. Which line arises if I go from 3 to 1? Don't be confused when I say one electron. Which lines arises if I go from 3 to 1? Is it C, B, or A? So obviously, these are the energy gaps here. And so this is the energy itself. That's the wavelengths, that is the frequency. You need to know now which direction the energy increases or decreases. And you tell me now, is it line A? If I go from here to here, is it line A, line B, or line C? Which one would it be? Why don't you think about it and give me your answer, please? I think that's where I stopped the last time. There are other people than you watching this lecture. There's a guy in Germany, for example, who wrote me. His name is Sven. Let's see if Sven gets this lecture, this answer right at home. Let's say all hi to Sven. Hi, Sven. Sven in Germany. He wrote me. Everybody click in? Oh, we're getting closer to the midterm. People start showing up. That's good. This morning I had 230 or something. That's pretty good, actually. All right, let's see. 74% say it's A, and a couple of people, about 66 say it's B or C. I do agree with the A's, and I explain it to you. Why am I agreeing with the A's? So, let's see what I got here. The frequency increases to the left, the intensity increases to the right. And so we had 1, 2, 3 bars there, 3 emission lines, and you were supposed to pick the right one. And I wanted to know, so if it goes from 3 to 2, this would be the smallest energy, wouldn't that be? That would be something here. E equals h times nu. Nu has to be small, or the wavelength has to be very large. Okay, this would be here. So that wasn't. That was what was that? That was C, wasn't it? That was C. So that wasn't it. Now then we can go from 2 to 1, 2 to 1, but there's also from 3 to 1. 3 to 1 is larger than going from 2 to 1, okay? So this must have been, D must have been here, and from 3 to 1, no, B, A, B, C must have been here. So that must have been the one with the highest frequency, or this one here. There we go. Here it is. C, B, see? Now the largest one is this one. This needs to be here at the highest energy because it reflects the energy, and there we go, and the answer was A. Good. Now let's make it a little more difficult. Now I'm going to show you 3 different energy level schemes, A, B, and C. And here is an emission spectrum. And I want you to tell me which is the energy level scheme that creates that emission spectrum. Is it A, B, or C? I'm giving you a couple of hints. This is drawn to scale, so this distance and this distance is the same. So if we would have an emission from here and an emission from here, would have the same wavelengths or same frequency or same energy, but it would be double, the intensity would be higher. So it would be just brighter, but that's not what you see here. You just see energy, okay? And this here, for example, and this here is identical, and this here is the same gap. So why don't you think about it and give me your answer? Four lines here. You have 4 lines here, okay? Now just look at how many transitions you can get from each of them, and then you can exclude the first ones, and then you look at the energies. That tests your combinatorial skills. Wow, we're multiplying. 260. Okay. Quantity is not necessarily quality, okay? It's unrelated what I said here. I think you need a little bit more hints, and you need to discuss this a little bit more. Let me see, okay. Now, how many transitions would you have from this one here? You would have 1, from this is 1, 2, 3, 4, 4 to 3, and 4 to 2, and 4 to 1. Okay, this is how many? 3. Okay. Now you can also have this from this here, 3 to 1, and 2 to 1. So how many transitions are those? 5. You see here 5 lines? No. Okay. Alrighty. So now we have a 50-50. You can call a friend. Call your friend next to you and discuss it. You can put it anywhere you want. No, dude, it bounces off the wall. It's good. This is the receiver, but it doesn't have to see it. So what's the answer? I think you are right. So was it? What is it? Mm-hmm. All righty, that's what I like to see. Excellent. If a 50-50 chance, it gets a lot better, isn't it? So the majority has B, but let's explain it. So what we had 4 lines here, okay? 3 in the high energy, very evenly spaced, and 1 in the low energy, okay? So how many lines would we have here? This was 1, and this is the same, so this is still 1, double intensity, that line, the lowest energy. This is second lowest energy, this would be this here. Third lowest energy would be this here. Fourth lowest energy, or second highest energy, would be this here. And this would be the highest energy, would be this here. So that would be 5 lines as we already established. Now let's go to this one. So this one, this distance, and this distance is the same, okay? This is the lowest energy, that would be this one here. This distance and this distance is the same, that's the second lowest energy, would be this here. The intensity would be double, of course, yeah? Would be brighter, just double as bright. Now, this here going from 3 to 1 and from 4 to 2 is also the same. So that must be the second highest energy. The second highest energy, that must be this guy here with double intensity. And then we have 1 for the big gap. The highest energy would be this here going from 4 to 1. So that would be this here. But this is not what I've shown to you. Okay? So this would have in the middle, these 2 green ones, so the middle would have a double line. I've shown you a single line and 3 lines in the high energy, and so this is clear. This is the smallest energy gap here, emits this energy, it emits it twice, but the energy is the same, so it's the lowest energy, it sits here, lambda is the longest, then this is the second lowest, okay? The second lowest is this here, and this here is the same. So we have double intensity, that's the second lowest, and, am I right here? This one here is the second lowest, okay? I'm sorry. This is the second lowest, this is this one. Then these 2 are identical. This goes from here to here, and this goes from here to here. That would be this one. And then you have the one with the highest energy, goes from 4 to 1. This would be this one. And with this, the solution was B, okay? So, we're going to talk a little bit more about waves today, and we're going to talk about the energy that these waves can have, what the solution of the wave equation is. And we're talking about the uncertainty principle first, and the uncertainty principle lies in the fact that you can describe either the particle as a momentum, or the wave here has a momentum or a wavelength, okay? So if you look at this, the de Broglie relationship says mass times velocity is momentum, and this is Planck's constant divided by lambda. So that's how we marry this. And now this is our wave function. This is a wave as we have seen it here. It travels in one direction. It's a one-dimensional wave, essentially. And you can describe this by a wave equation. We call this psi of x. X is the x direction. And it's a sinus, a constant times a sinus times this expression here. This is how you mathematically can describe this wave, okay? That's all there is. There will be another test on this, okay? I just want to make sure that you understand that. And so now I have a wavelength here, and the wavelength is the same. It's lambda, okay? It's from here to here, from here to here, from here to here. That's always lambda. So I know its momentum very well, because I know h and I know the wavelength. So I know exactly what momentum that electron, and we are talking about electrons now, what momentum this electron has. But the problem is, I don't know where it is. Okay? So if I take this and square this, I take the square of that wave function, so I get all positive lobes, and this gives you a probability distribution. It can be anywhere where it's above 0. You see that? The electron could be here, the probability here, anywhere it is. So if I know the wavelengths very well, or exactly, I can't tell you where the electron is. Okay? So now, that's a dilemma. So it excludes each other, the particle nature and the wave nature. And so do you have an uncertainty in position of that electron. Now let's do the opposite. Now I'm going to make a wave function where I know exactly where that electron is, or very well where the electron is. So that would be a funny looking wave function. So here there would have very little probability here. Let me see. But I have a known position. I put that here, okay? So it's very likely there on my x-axis. It's very, because I have the highest probability here. But in order to describe mathematically, in terms of wave expression, to describe such a structure, such a wave, I need a whole bunch of waves in order to do this, and I need to add them all up till I finally get to something like this. So the expression now for that wave equation, is the sum of a whole bunch of waves with all kinds of different wavelengths, till I get finally to something like this, okay? So now I know the position very well, but now I have a whole bunch of wavelengths. So I don't know the wavelengths very well. And this is what is, if I square this here, then I have very less likely to be here, but very high probability that you can find the electron here. So, and this is sort of mutually exclusive. You either know the wavelengths relatively well, then you don't know the position, and if you know the position, you don't know the wavelengths very well. Okay? And this is the guy, there's an uncertainty in the momentum, because you have here now all these different wavelengths. And this is married in what is called the Heisenberg uncertainty equation. The delta of x times the delta of the momentum, the delta of the location times the delta of the momentum, can't be smaller than a fixed number. And that fixed number is equal or larger than Planck's constant divided by 4p. So you don't need to remember that here, but you need to remember that if you know the location, you don't know the wavelengths. If you know the wavelengths, you don't know the location very well. There's a limitation for that, okay? All right, so you have heard about the Heisenberg's uncertainty relation of waves and particles. So now we're coming to Schrödinger. Now I'm not trying to scare you. I'm not going to do much math here, but you should have at least one time in your life, except in Jeopardy or become a millionaire, what is a Schrödinger equation? At least you should have heard it for once, okay? The Schrödinger, he actually is the father of quantum mechanics, essentially. He said, I have these waves, and I have these wave equations, and I want to relate the energy. What kind of energy, all kinds of energy levels would these waves of electrons have? And so I need to solve this and get a whole bunch of energies for a certain wave function. And so we can say the electron has kinetic energy, which is the wave function. You would take the second derivative towards the distance, x, and you have a bunch of constant. Okay, that's how you can derive or can describe the kinetic energy of this wave. This wave is now an electron, okay? But it also has potential energy. That's also the potential energy in terms of the direction times multiplied with the wave function. So, and this gives you the total energy of that electron and the wave function itself. That's a differential equation. That's all there is. And so you write this, and this is the form of the Schrödinger equation. You say this is a Hamiltonian. It's a mathematical operator. It says, you call this H, and you define what H is. Do a bunch of mathematical operations with the wave functions, and at the end, you will get a bunch of energies and the wave function itself. So that you solve that equation in terms of the energy. All right? So this is all you need to know, and you don't need to be able to derive this. But if you look at this, the energy is essentially, if you look at this wave here, and we've seen this as a box here, we see the kinetic energy is actually zero along the wave. Only at the ends, its maximum, did I say kinetic energy is zero? No, that's wrong. The kinetic energy is, we described that wave with the kinetic energy, and the potential energy is essentially zero along the wave. Only at the ends, it has maximum amount, all right? This is called particle in the box, and we call the length of that box, in this case, we are here, we see this as a big box where that wave goes back and forth, goes from 0 to x to L. That's the whole length of the box, all right? So that's, you wonder why this L gets in here. So if you do this, you get this kind of an equation, and at the end you get the energies. And this is something which looks very, very familiar to you already, essentially. It's the energy of the nth level. So those are the different energies that that electron can have. And the nth level is your quantum number, your main quantum number 1, 2, 3, and so on. And this is h squared, it's a constant, that A times the mass of the electron times the length of that box. Don't worry, it's a constant, all right? But what is not a constant is n, and the energy is not a constant. So the energy, and I need to give you that other board here, because I'm going to ask you a question very soon. So the energy is proportional to the square of the quantum number. All right, that's the first thing we have. And if we take this here now, if n equals 1, and this is a constant here, is that constant times 1. So that would be the energy level here, and that must be the first level, so the energy would be right here. The wave would look like this. We know this already. Come on. It would like this, and this would be the probability distribution, the squared of that wave function. So what would be the next one? If n equals 2, what is the energy? Is 4 times that constant. So that would be a full wave, and the probability function would look like this. Okay? It's not here, but it has to be here. It can be here and can be here, but it's not here, the electron. Okay? Now n equals 3, that would be E3 is constant times 3 squared is 9. And then we go to 16. So this is the probability function. And there you go. And this goes till infinity, essentially. All right? So we call n the principal quantum number. And I've shown you this with the spectra earlier. This is the same thing, but now we're going to put some real values on it, not just wavelengths. En, the energy is minus z squared. What is c or z? The atomic number. The atomic number squared divided by the principal quantum number squared times a constant. And this is called the Rydberg constant. This is that constant I was just talking about. If you bunch this all together, you get an energy, and this is called the Rydberg constant. The Rydberg constant for one electron is 2.18 times 10 to the minus 18 joules. Now, if I have a whole mole of electrons, which is more likely to have than one electron, I multiply this with Avogadro's number, and I get 1,312 kilojoules per mole. That's an energy, kilojoules per mole of electrons. All right? So our energy comes in here, and the value of the energy, the level will be decided by C and by N, and this is for one electron at the moment, one electron systems. Now let's have a look. The ground state is, and what atom are we talking about? If I get this as the ground state, what atom is that? Why is it hydrogen? Z is 1. Okay, good. So it's minus c squared is 1 squared is still 1, divided by n squared, and n is 1, so this is minus 1 divided by 1 is still 1 times the Rydberg constant. That's the ground state. Now the second one is minus 1/4 times R infinity times the Rydberg constant. That's now a real energy, okay? The third one is minus R9ths, and it goes on, and the levels get smaller and smaller and smaller till it goes to 0. You notice this is a negative number, okay? This is how we define it. The lowest possible state is the largest negative number. You can define anything. You can put the 0 any way you want. Why did we do it this way? So the number gets larger and larger and larger. You get in higher states. At the end, you get to 0, because you will have 0 energy of that electron when it's not related at all anymore to the nucleus. If I, for example, have here my nucleus, and I go out to one state, and 1, 2, 3, 4, 5, and I go further and further away, the less and less it will be influenced by the attractive charge of the nucleus, the electron. Okay? And when it's totally gone, then the nucleus has no influence at all on this electron, and it will be 0. There will be no energy. Right? So, and you can see that the levels get smaller and smaller and smaller because you're already so far out that it really doesn't make a whole lot of difference anymore in terms of energy. All right, so this is we have this negative number for the ground state. So I have given you this information. Can you all read this? And I'm asking you now, I have the hydrogen atom, which has a level scheme like this, okay? Minus R and minus R4. And I want to know from you, this is the level scheme of a different, it's a one electron system. I'm asking you now, is that one electron system, is this helium plus or lithium 2 plus? Lithium has 3 electrons, I take 2 away, I still have 1 left. Or helium has 2 electrons, I take 1 away, I have 1 away, I have 1 left. So these are all one electron systems. So why don't you think about it and give me your answer? Which does it correspond to? Now, we are not looking at light absorption. We just determine the energy levels without having absorbed light. Light absorption would be an analytical probe. We just can tell what the levels are before we do anything. If it's hydrogen, it has this kind of level energies. If it's helium plus, it has these kind of level energies. If it's lithium 2 plus, it has these kind of level energies, or energy levels. Okay? So this is complementary what we're actually doing now. Now we're going from the scientific side, not from the analytical side. So some people pay attention, a lot of them, because they didn't say, he showed me hydrogen, so the other one can't be hydrogen. It's a very good thing, okay? Maybe I should have put hydrogen plus, which has no electrons. So why don't you just go and see if you can fit this game? Just use helium and see what levels you get, and use lithium and see what levels you get, and you have the answer. You have to do it twice. I think you have to do 2 calculations maximum to get it, okay? So discuss this with your neighbor, please, and the person behind. There's a lot, 50% have it wrong, okay? No, if 50% have it right, let's be positive. Some people must have left. About 40. Okay, excellent. Very good. Very good. Let me explain it. You just have to put the number in and that's it. Okay, so we had hydrogen here. That was minus R and minus R quarter. A quarter of a Rydberg and 1 Rydberg. This is this, okay? Now, let's see what we have here. This is our formula. Let's do it for lithium. Lithium would be minus 3 is 9, and N equals 1, minus N equals 1. Minus 9R would be down here, isn't that right? Minus 9R, okay, that's not it. All right, so let's do helium. So helium would be 2 minus 4 divided, minus 4R would be the lowest one. This is minus R, and this is about 4 minus R, 4, let's see. N equals 1. Minus 2 squared is minus 4, so at minus 4R would be the first one. Okay? The second one would be, what would be the second one? 2 minus 4 divided 4 minus R, okay? Wait. What's the next one? So what is this minus R fourth here? Huh? Exactly. So this is correct. So this is minus R fourth here. Yeah? Okay. And this, okay, good. All right. So you got it. It would be helium. Yeah? All right, I need coffee. All right, let's do another one. Which transition in helium has the same wavelengths as 2 to 1 in hydrogen? That's obviously hydrogen, isn't it? Yeah? We established this now. This is 2 to 1 in hydrogen. Which transition in helium has the same wavelengths as 2 to 1 in hydrogen? Is the 2 to 1 transition, the 4 to 1, or the 4 to 2 transition? Think about it and try to give me an answer. It's getting a little more complex here. Now we have more people again. So you need to click it consistently to get your points, okay? Please don't forget. Otherwise, I don't know that you were here if you don't click. So, what is the answer for this? 4 to 2. 4 to 2 is the answer, yes? That's exactly right. You guys got it down pat. And so, with this, I'm going to explain it to you at the beginning of the next lecture for those who didn't get it right, and the answer is indeed, it is 4 to 2. See you on Wednesday.